Right. Hello, everybody. All right, I got a response in chat, so it looks like you can hear me. Um, just let me know if there's any problems in the YouTube chat or on Piazza or in the Slack channel, but if it seems like I don't see it, then do it somewhere else too. So, so the main topic is problem set 14, which is getting into NP-complete problems and primarily the idea of polynomial reductions. So you've all had a chance to look over the problem set and the solutions by now. I'm just going to go through and address questions from the office hours Piazza thread, try to make things clear and give some intuition for how I think through these. I know last time I streamed, we had some issues with not being in focus, so I wrote out some pages ahead of time, and I scanned those already, and they're linked in Piazza, so you can open those and follow along that way if focus is an issue again. Uh, all right, first things first, Angelina had some questions about input size and polynomial time in terms of what. So let's get set up here. Making sure this looks okay. I can't see that very well. If I up the bit rate, can I see it better? All right, well, the display doesn't look very good for me. Hopefully it looks better for all of you. And if not, that's why I scan things ahead of time. So is how do we define input size? So for all of these, we're taking in, specifically for a reduction where you're reducing from one NP-hard problem to another. The input to an NP-hard problem is a string, and so your input size is the length of that string. And so typically that string will be an encoding, like if it's the clique problem, it will be the string encoding of a graph. You can then, so that is what we mean by length of input. So yeah, it's the string of the length of the string representation. So if it's like 3 CNF sat, that would be the clauses that we're satisfying. Yeah. Okay. Let's try to focus a little more. As the number of literals as well. So everything written out. So it's like if it's yeah, plus the ands and the ors. So just So it's when you write out everything. So if it's a graph, you could be representing that as an adjacency list. It would be however many characters you write out in the adjacency list. So really, and then if you start doing an algorithm that runs in terms of the number of nodes in the graph, then I think the easiest thing to do is say the number of nodes in the graph is less than the size of the input. So if you're polynomial in terms of nodes or nodes and edges, then you're polynomial in terms of the length of the input. And that's kind of all of these. So the input size is the length of the string. The polynomial time requirement is in terms of the length of the string. And then so kind of the first step in a lot of these, I have this from my notes from last semester. It's in a few of the solutions. It's kind of what I wrote out here. This is this was the first line that I wrote on the problem 2 for the exam. Given the input string x, the first thing we do is decode x into the data structures for the problem, whether that is the clauses and the literals, or whether it is turning it into the graph and k if it's the clique problem. So you need to know the nodes and edges in k. And then you usually have in here like a sum where if your input doesn't decode to something, then your input is not in the class. So you decode it to some default representation that's not in the class. Does that help for this question? Or any questions on that section? Okay, if you're trying to reduce from 3CNF to graph, okay, yeah. So the input size we're talking about is the input to, well, so it's specifically the input to the reduction. But if you're reducing from 3CNF to a graph, the input to the reduction will be the 3CNF sat, which you then decode and then do some transformation on that to build the output of the reduction would then be the input to the graph. Now, if your reduction runs in polynomial time, then your output cannot be more than polynomially larger than your input, because you have to take 1 unit of time for every character you write to output. So as you're building an acceptable reduction, your relation between the input to CNFSAT and the input to clique or another graph problem will be a polynomial relation. So since we only care about things asymptotically, you can kind of hand wave that away. The strict thing that we care about is the input to the reduction, which is something in the format of the problem you are reducing from. Any other questions? All right, then I am going to move on. Input, I would count that as linear because you have to copy the entire length. It doesn't really matter because copying the input will never turn your problem from polynomial to not polynomial. I can't think of a case where you would be copying the input an exponential number of times, but yes, that would be linear. So yeah, moving on, had some questions about differences between the book and the problem sets and how specific ways that things are represented. So now that you have the practice exam, the simplest thing I would say, I would recommend getting familiar with the problems that are listed on the practice exam as ones you can assume are NP hard, and try to use those formulations. Now, so that the specific question was the problem, as stated in the problem set, said that the Hamiltonian path problem is NP complete or NP hard, I forget which it said, but it doesn't matter because we're just in the problem, we're just reducing that to Hamiltonian cycle to prove that that is NP hard. But in the book, we have an ST Hamiltonian path instead. And so I just wanted to talk that try to use the general one because that's what's listed on the exam. That being said, like they are closely related, so I kind of want to go through some how they're related. So here I just formal reduction for these, but just kind of reduce one to the other in both directions to show that they really are equivalent. So this first example, I took the graph from page 292 of SIPSR that has for the ST Hamiltonian path problem. So Chris, in this case, I'm mostly saying NP hard because I'm not touching on showing that a problem belongs to NP. I'm not getting into the verifier problem. But yes, everything that we're talking about is NP complete. I'm just talking about the hardness problem, the side at least as hard as everything in NP, and not the side that does belong to NP. As Chris probably mentioned, problem one will be showing that a given problem belongs to NP, and then question two will be that the same problem is NP hard. So collectively we'll show that it's NP complete, but that will be in two questions on the exam. So you don't have to do both pieces on one question. One note, so going back to the graph, one note, I just made this an undirected graph instead of directed, which makes it easier to find a Hamiltonian path, but because that is undirected, I just made that simplification. So on the left here, we're trying to find a Hamiltonian path from the source to the sink. So we're finding an ST path, and I mean, there's a number of them in this graph that work. It's not hard to find one, and so what I want to show is if we want to then make a new graph that has a Hamiltonian path starting and ending at any two nodes, only if the original graph has an ST path, then a modification you can make to the graph is to just add two new vertices and have one of them connect only to S and the other connect only to T. And then if you have any Hamiltonian path in this graph, it has to start at this node and end at this node because it has to visit them, and you can't node and then leave it by another path because there's only one way. So any Hamiltonian path here will include an ST Hamiltonian path in the original graph. So that's kind of how they're equivalent in one direction. Kind of a higher level, just if you have an ST Hamiltonian path and you want to find if there's any Hamiltonian path in your graph, in that particular graph, and you only have the ST algorithm, you can just a pair of vertices, and that'll add n squared to your runtime. But that if ST ham path was polynomial, then general Hamiltonian path would still be polynomial. And then kind of going back the other direction, if you want to say that in your input graph you have if you want an ST Hamiltonian path in the graph you're constructing, and you have any Hamiltonian path, then you can create S and T and connect them to everything. Yes, because then now over here, we are requiring you to start at S and end in T. So you go from S into the graph somewhere, go through the graph, hit all the vertices, and then at the end, leave and go to T. So in the original graph, wherever you entered the original graph from S and wherever you exited to T, that is a Hamiltonian path in the original. So that's just kind of how I would go back and forth between and the general case. And speaking more generally about reductions, so I know I've had a number of questions on the thread about how you know which problem to reduce to show is NP hard. And the way I do that is of the list of NP hard problems that we can assume are NP hard on the exam, what is closest to the problem I'm trying to solve? What is going to require the smallest modification? So, so for instance, I'll cover this later in more detail, but like the dense subgraph problem 6, I believe, we're trying to find subgraphs of a graph that are at least as dense as some constraint. So I look at that and I look through kind of what are, is that similar to 3CNF SAT? Not really. It's a graph problem, so it's probably easiest to reduce another graph problem to it. And then what I settle on is reducing from the clique problem, because it's about finding dense subgraphs, and a clique is as dense of a subgraph as you can get. So it seems likely that we can make some modification to a graph that has a clique so that the dense subgraph is a subgraph of high enough density only when there's a clique of the right size in it. We can, and I mean, there's other examples. So let's see. So like for I know I'm probably stepping on the next office hours a little bit, but the subgraph isomorphism problem, that was another one where what seemed to make sense to reduce to it was the clique problem. So, but I'm not saying reduce from clique on the exam, because I haven't seen this semester's exam yet. But if clique seems like it's the most similar problem that we can start from to what we're trying to prove, then start with that. But it very well could be something completely different, and then you might want to start from a different problem. Any questions on that section, and just kind of how you think about how different problems relate to each other, how you go back and forth. I guess while we're here, I can also mention how we go from either of these to Hamiltonian cycle, because that was what the reduction we were actually trying to do in the problem set. So if you have the general 3 CNF SAT to everything, I think that's a relic of, I believe, like that was like the original in complexity was reducing 3 CNF SAT to a bunch of other problems. I would say on the exam, unless it looks really similar, unless there's an obvious way to reduce 3 CNF SAT to it, like the problem of reducing 3 of CNF SAT was NP hard, seems like you should start from 3. But if it doesn't seem close to 3 CNF sat, I would try to reduce something that looks closer to that instead. Um, there are problems we haven't seen. Yeah, I would expect SIPSR and the lectures and the problem sets to cover potential exam problems. I mean, it's very possible that there's a problem you haven't seen before, that we'd seen subgraph isomorphism anywhere before it showed up on our exam, but the should adequately describe the problem on the exam. Um, and it should be something that there's something similar-ish in your toolbox that you can reduce from. So I would not say that it's necessary to go research a bunch of reductions that you haven't seen covered in class. Yeah, exactly. Rule of thumb: look for similar problems. Um, so like real quick, going from Hamiltonian path to Hamiltonian cycle. Um, if you're working in the general case where you might have a Hamiltonian path starting and ending from any two, then that's the case that Chris gave in the solutions. You just add a new vertex that connects to all of them. So then and then if you just delete that vertex and the two edges connected to it, what remains is your original graph with the Hamiltonian path, because you had to go through the extra vertex with one step. I think Angelina asked how you come up with those, like adding a new vertex versus like just adding an edge, adding new edges to the graph. I mean, really, what I would suggest for figuring out that is make a really small example and just write it out and try the reduction that you're thinking of. And it's not a substitute for a proof. I would just do that on scratch paper, but it can often help you figure out, like, oh, there's a really obvious way that my reduction doesn't work, and then how can I change that to fix it? So ST case, this is a little bit easier to see, maybe, because the obvious modification to make is put an edge between S and T, and then if you have an ST path, you have a Hamiltonian cycle, because you can get from T back to S. The problem is that you might not have a Hamiltonian cycle. I forget exactly why that broke down, but it caused some problem where you might have a Hamiltonian cycle in the resulting graph when you didn't have a Hamiltonian path, in an ST path, in the original. But so the modification then is to add that new vertex and connect that to S and T, because that forces your Hamiltonian cycle to go S new vertex T. And so then if you remove the new vertex and the two edges, you're left with an ST. Oh yeah, yeah. I remembered that I gave an example that failed, but I didn't write that down here. Okay, I'm gonna move on, spending some more time just on how you come up with these things. So I wanted to go to the reduction from 3 CNF to 4 CNF. Yeah, that's right. That was the simple example that failed. The square with the corners. So just again, like kind of, this is just kind of my thought process of how I would modify um, 3CNF formed statement to have this to be true in exactly the same cases with 4. So, I mean, I kind of break it down like be true. Each triple has to be true. So in my after my transformation, I want to take consider each triple separately and make and have this be true, have whatever comes into be true only when this is true. And so kind of the first idea that comes to my mind is, well, let's add false to it. Um, we can't add false as we can't add something that's false. We have to add something that could be true or false. So there's a couple ways that you can kind of fix that up to make it work. So one way to do that is to expand it to 2. One that has a new variable w, and one that has its negation. So one of these will be true no matter what x, y, and z are, but the other one will have, because say w is true, then w not w is false, and this has the exact same value as it did in the original. If w is false, then this one you just cross out, and this one matches the original. And but that's not the only way you can fix it up. So the other way that I thought was really clever was you just pick your new one, W, or you could even call it F, because you want it to stand in for false. And then if you just add or one new clause that is the or of not F 4 times, forces this has to be satisfiable, then not F has to be true, so F has to be false. And then and the thing I really like about this is that if your 3CNF is really long, you don't have to all of them. You're just adding one new clause. But anyway, that I think that's a fairly obvious example, but it's still just kind of how the thought process going through it is. What is a similar? What do I need to do in the new domain to be true exactly when my original problem is true in the old domain? And so in this case, when you have a bunch of true false statements ANDed together, you want each statement to have the same truth value, to transform into something that has the same truth value in the new domain as your original statement did in the old domain. Questions on this section? I'll move along. Feel free to jump in at any time, though. I can go back. Um, so problem 1 has a bit of a hard to follow reduction in the solution that Chris gave. So I wanted to just work through with pictures the example that Chris gave, and then kind of talk about the logic going into it. Problem is we want to reduce from the independent set problem to this matching with forbidden edges problem. So the first step of Chris's construction is, so if this is our original graph and this is the one he gives as an example, there was edge was missing in his solution. He mentioned in the problem set problem that should have been an edge in the original graph. So I've drawn that in here. So this is your original graph. You have five five vertices, and there's a among four of them, and then the fifth vertex, vertex 2, is disconnected from the rest. And the only other edge that's missing is this 1, 3 edge. So the first step of the reduction is we're looking at independent sets. So in this graph, the maximum independent set has size 3, and that is 3. And you can't add in 4 or 5 because they're connected to 1 and 3, and you actually can't switch out 4 or 5 for 1 or 3 either. So in this case, this is the only independent set of size 3 in this example graph. But this reduction has to work for all cases, but I'm just going to talk through the example because it's a bit complicated and try to get at what he's doing. So the first step is for drawing this out, is just take the complement of G, because we're going to be kind of blowing up the graph, but we're going to end up with one edge from each of these. And then the step that I know I found really confusing the first time I read it was that we're constructing our new graph to have n-1 copies of every vertex. So in this case, we have 5 vertices in the original graph, so we have 4 copies of every original vertex here. But really, all this is doing is letting you edges without having them share vertices. So for the matching purpose, we will never have edges that can't be part of a matching because they share a vertex. And the number of edges is by building this set C of forbidden edges. So that's just a side example of why we do n-1. So I just did 3, but if your original graph is n disjoint vertices with no edges between them, then your constructed graph will have all of the vertex copies connected to every other. So in this case, we have 3 vertices, and there's no connections between them. So the complement of G then would be this, 1, 2, 3, and then they're all connected. And then we want none of these edges to share vertices. Hence, we have 2 copies of each vertex. And so up in here with 5, if there were no edges here, then this would be a clique, and we would need 4 copies of each edge. The vertex would have degree 1 instead of degree 4. So before we have forbidden edges, we can, the matching is every single edge in the graph. So in this case, there would be 5, because there's 5 edges in the complement of G. And now the key is that if for this reduction, the K for the independent set, in this case, you would have K equals 3 because that's the biggest independent set in G. And then after the transformation, your new K is not the same as the old K. It's K choose 2, which is the number of edges that you can put between the vertices of your independent set in the original graph. So it's pretty clear before we start forbidding edges that we'll always have one edge that for every edge that's between the vertices in your independent set. In this case, it's these that I've circled, and then we want to build our build C for forbidding the edge pairs, so that to basically force us to choose this set of edges and not to also include these. The way that we build this is we say we put in a pair of edges in G prime if any of their original vertices are adjacent in G. So this is kind of down, but I've underlined what caused all of these to be in here. Um, so this first one, we look at this 1-2 edge and this 2-4 edge, and that's not allowed because 1 is next to 4 in the original graph. So you can't pick both of those. And similarly, 1-2 and 2-5 can't be both picked because 1's adjacent to 5. Because 1's adjacent to 4 again, 1's adjacent to 5, and then 3 is adjacent to 4, and 3 is adjacent to 5. And we wouldn't really have to do anything here if all we had to have was a big enough matching with forbidden a big enough matching in G prime. But we have to put in all the work to prevent there from being that big of a matching in G prime if there wasn't that large of an independent set in G. Questions on this? I know it's a bit convoluted. I had to read it 2 or 3 times to figure it out. I would expect that this problem is harder than you would see on the exam. I don't write the exam, so I can't promise that, but I would not expect it. 2 edges are adjacent. For the purpose of going back to 2 edges can't be in a matching if they share if they're adjacent. So yeah, so 2 edges matching and not a matching with these extra forbidden edges. Then all of these, none of these would be adjacent because we made these duplicate vertices, so none of them share a vertex. The 3 edges that I've circled, these are the ones that this is your maximum matching with forbidden edges when this is the forbidden edge pairs, and this is exactly the edges that are between copies of the original vertices in the independent set. So these circles match these circles, and this is what you'd come out with. So in this case, K is again, but that's not 3 as in the same K as over here. It's 3 as in K choose 2. Reduction running time, I would say reduction, you have n minus 1 times n, so it's n squared to construct your new vertices, and then you're only constructing 1 edge for each edge in the complement. I suppose that's again order of n squared. So constructing G prime, n squared time for the vertices, n squared time for the edges, and then constructing this. So this is going, you have to check every pair of edges against the original graph to find out if that pair is going to be forbidden. So that is in terms of pairs of edges, and I suppose the upper bound on that, if we had no edges in the original graph, would be n to the 4th. Actually read Chris's runtime analysis of this reduction. Yeah, there's an n squared and an n to the 4th term in there, and there's some other things going on too. But yeah, I don't think there's a choose 2 in there, though that, or yeah, that, I think, yeah, that choose 2, oh yeah, no, that's the end of the 4th term, sorry. Yeah, so yes, it's on the larger side, but it's still polynomial, and that's all that's required for these problems. More questions on this? Um, well, the tricky thing is, um, concern with saying with giving an order of n to the thousandth bound is then you're that doesn't really force you to analyze the runtime of every section. And the problem with that is uh, is that your reduction can't say solve the independent set problem in order to decide what reduction to build. So if you just give like a loose polynomial bound like that, I'm not could lead you into trouble because that would lead you into trouble because um, you might miss that you're actually including a decider for an NP hard problem in your reduction, and then that is not something that you can do NP. But if you prove P equals NP, then that that's you're on a whole new level, and you get much more than just a 5 on the question. You get $1 million and probably a Fields Medal and um, international fame. But so assuming that you don't prove P equals NP, um, I would give a tight runtime because otherwise it's easy to slip in something that is sneakily not polynomial. Now, if your reduction takes does has a factor that takes n to the thousand time to run, that's okay. That would still a I think Fields is the math medal. I You might get a field. I don't know. You'd get some very prestigious award. Yeah, I mean, prove P equals NP or prove P not equal to NP, and you might win them both. Um, I mean, I don't think there's ever really going to be a practical reduction that's order of n to the thousand. You could make a reduction that takes that long by intentionally wasting a bunch of time. Your reduction runs an n to the fourth, and you stick it in a n to the 996 loop. Um, I would argue the tightest. I would just try to give a tight bound. I'm not sure exactly how the runtime is going to be graded, but I would not suggest, you're just exaggerating, but I would not suggest giving a looser bound just to be safe. It is technically correct. More questions on this section. Right, yeah. If you have the wrong bound, then the justification is difficult. If you think that something is n cubed or n to the fourth, um, I would say I would write that down. I would write down that I'm not sure if this runs n cubed or n to the fourth, but it's definitely one of those, and therefore it's polynomial and acceptable, something like that. Um, yeah, that's what I would suggest in that specific example where you're a little unsure about one section, but you know that it's still polynomial. All right. So I wanted to just walk through kind of the whole process of um, graph problem. Let's see. It doesn't seem to be showing up well. Um, yeah, so this is really just to give me an opportunity to kind of walk you through my thought process with trying to solve a problem like this. So like we're given this problem with the density of a subgraph. It's defined as you have a subset of the vertices, and the subgraph is just all of the edges that are between vertices in that subset. So that is the subgraph induced by S, and we define the density of that subgraph as the number of edges in the subgraph divided by the number of pairs of vertices. So it's what fraction of possible edges are present. So the dense subgraph problem is a language of strings. So this going back to the length of the input. So the input to the dense subgraph problem is a string. And we decode that string into a graph and an integer and a floating point number. Runtime analysis in terms of, the size of the graph or the size of k. Well, no, the size of k would be bad, though. I would do it in terms of vertices and edges, and you know that v and e are both smaller than the size of the input. Um, Seems like it's still fuzzy. Again, this is did scan and upload a copy of this page. The size of the input for floating point number, that would be however many bits you use to represent it. So yeah, we'd probably just say that it's a 32-bit or 64-bit, and then really it too much. Um, but yeah, it's the size of you can really think of this might help. So the size of the input would be the size on disk. So if I define this graph and integer and floating point number and made it a triple in Python, and then I said, dump that to disk, pickle.dump tuple, then how big is that on disk? And that would be the size of my input. And without getting into compression. Um, but yeah, I wouldn't be overly concerned. So it's fine to consider it a constant. We can say that it's a 64-bit, and then but that's we're only considering things in multiples of 64. If k is an integer, well, so k the so we don't generally get this in the weeds, I would say, but we can put an upper bound on k because right, we can put an upper bound on k because it doesn't make sense if k is bigger than the number of vertices in the graph. So you already have to have um, you already have to have at least size of k in your input because your graph has to have at least k vertices. Um, we can put in wouldn't worry about handling these special cases on the exam. But if you're being super formal about it, you could put in like a check at the beginning that you decode G and K, and if K is bigger than the number of vertices, you immediately reject, and then you don't get into having to worry about um, K being too much larger. Um, so so kind of so our goal is to prove that the dense subgraph problem is NP complete. So the first thing we have to do is belongs to NP, and I prefer doing this with a by building a deterministic verifier. You can also give a decider. So the input over here, we have to define our input and our certificate, and then what the verifier does on that input. The input is just a member of the language of that subgraph, so it is GK delta, and then if your input doesn't decode to GK delta, like if you try to do this in Python, it would throw an error. Then for your verifier, you just decode it to some default state that fails verification, no matter what your certificate is. So like an example, you could set this to a graph with no edges and delta greater than 0. These defaults here, this is what Chris used in his solution. I'm speaking more generally. Like I think that's what I would use as my default. Is like 3 nodes and k equals 3 and no edges. Your certificate is the node is a string that you decode into the nodes that are part of. It should be S. It's the subset of nodes that induce a subgraph with at least k vertices that has density at least delta. And you set that you have a default you have a default for the certificate where if it fails to decode to something sensible, then you default it to it's empty list. So you haven't provided any subgraph, any subset of vertices, and would reject. So then the real work is in building the verifier. In this case, your verifier initial check is S smaller than K, or is it smaller than 2, where your number of where is undefined, then you immediately reject. Otherwise, you go through and you build the subgraph induced by S and compute its density, and then you reject if the density is too low, and otherwise you accept. So now we've built the verifier, and then the remaining steps to have a complete problem, the verifier is correct. So you would say if your input belongs to the subgraph and S is a description. Let's see, how did I write this out? Or correct. Yeah, so if if your certificate is a list of vertices that induce a subgraph that passes, then it's clear to see that the verifier will accept, because your certificate will be a subset that's big enough and has high enough density, and those are the two things the verifier checks, and it accepts it correct. And then I guess in this case, the easiest thing to do is probably prove it. Prove that if your verifier accepts, then your input belongs to that subgraph. Like for I know, Angelina, you asked for like, how do I know whether I prove kind of L, you know, input. Well, I guess that was on the NP hard side, but kind of, do you prove that, you know, thing in L implies that f of thing in L prime, thing not in L implies that f of thing not in L prime, or do you prove the contrapositive of that second one, where if f of thing is belongs to L prime, then thing belongs to L. Um, I don't. I would say there's not a preference. I would do whatever is easiest for you. If you start trying to prove one direction and it seems really hard, that would be a clue that maybe it was intended for you to prove it the opposite direction. There are plenty of problems where proving it both ways works fine. There are certainly problems where proving a statement is much easier than its contrapositive or much harder than its contrapositive. Um, so yeah, do whatever you're most comfortable with, and if it seems really hard, try the other way. Um, but yeah, so then the last thing you have to do to prove that, if you're doing the verifier method, is show that v is polynomial time in terms of this input string. And then the other side is proving that dense subgraph is NP hard, um, to reduce a known NP hard problem to dense subgraph. And I kind of mentioned this earlier, but I'll just go over it again. So kind of my initial thought is from this list of problems that we know are NP hard, that have been given, that are allowed on the exam, what is to dense subgraph? And for this problem, they're not all going to be as obvious as this, but the description of the problem mentioned that clique is the densest subgraph at density 1. So that's a pretty big clue that clique is going to be easy to reduce. Okay, question. Is it correct to let the verifier reject if input certificate is not of expected form? Yeah, well, so certainly if the input is not of the expected form, then then it cannot. If your input is X that doesn't decode to this, then X does not belong to dense subgraph, because dense subgraph is a language of strings that decode to this form. So if they do not decode to this form, if X does not decode to this form, then it cannot belong to dense subgraph. So our verifier should reject. Um, I'm not sure what you mean, do we need to check for the input in the verifier? The certificate is of the wrong form. Well, if the certificate is of the wrong form, then the certificate is how the verifier verifies that. If the certificate is of the wrong form, then it does not describe a solution in the input. So the verifier should reject. Because if the verifier could determine the input with the wrong certificate, then it would be a decider, and we would have is in P. Right. I Okay. I understand what you mean. I'm not. I know. Like I did it that way because that's how Chris did it in his solutions. I'm not what the reason is for having defaults that will fail instead of just failing. Um, it comes out the same in the end. There's probably some um, for doing it this way, with building defaults that will fail on the verification. Um, sure what that is. In this case, do we need to check that G is a graph, K is an integer, and delta is some floating point? Yeah, so I would say that check is kind of is assumed in this when you say it decodes. So when you say that X decodes to this, when you decode, you build a valid graph and integer and floating point number. And if any of those fail those checks, then you immediately use the default. So yeah, your input validation happens in that decoding step. Um, yeah, more work on the exam. I think it would be safest to follow the pattern that Chris has established. That being said, I don't see us being particularly picky about that. I don't know if I'll be grading problem one, so don't hold me to that. Um, if you have the time, explicitly state it because that's the most clear. Um, if you're really rushed for time, that's not where I would spend your time. Um, General test tip for this in particular, I found it really helpful to write out a full to write out like a full reduction. I don't think I wrote out a full verifier, um, but like I wrote out something on the cheat sheet, and actually on my solution, this you have to be a little bit careful. I'll show you. This is the first page of my subgraph isomorphism solution from page 2, and this whole step 2 was something that was necessary in the problem I had recorded on my cheat sheet, but was not necessary for this reduction. So I ended up having to cross it out and left a little note saying that this was from the problem I was basing it on, but I didn't need it here. So um, the grader definitely knew that I was basing it off of something else that I had seen directly. But that was something but it helpful to me, and I would recommend it. So yeah, I'll just finish going through kind of my thought process on designing this reduction from clique to that subgraph problem, and then we'll wrap up there. So as I mentioned, like the problem statement mentioned a clique in there. Yeah. So that's how I decided to reduce to clique from clique. So the input to clique is something that decodes to a graph, and k for the size that it has a clique of at least size k. So the first question I ask is, can I use the same gk from the input to clique in that subgraph, or do I have to modify g, or do I have to modify k? Um, and this is where I would draw out like a 3 or 4 node graph and think it through, with working an example. Um, and I convinced myself that the original GK can probably work. So then, what delta needs to be? Um, I mean, so the the thought process there is you know that you need delta to be um, close to 1. And honestly, if you said 1 like you did, Angelina, in your original solution, I don't see that. I don't see that losing points on the exam, even though technically delta has to be less than 1, um, because you definitely got the idea right without getting the specific of how you delta big enough. But the idea is, so we need delta to be really close to 1. Um, only cliques will be bigger than delta. And so figuring out the 2m over s minus 1, um, that, I mean, really that's just that just comes from this formula where I just say the biggest that this can ever be, um, when it's not a clique. And so the biggest non-clique is start with a clique and delete a single edge. Um, Now the key is that would, um, I think you only have to worry about that for k. You could probably use k instead of n. N is just safe because it says, because if you do it in terms of n, then no non-clique will be bigger than delta. Whereas if you do it in terms of k, you could have a bigger non-clique, but that would have a clique that is one node smaller. So if you're doing it in terms of n and n is strictly greater than k, then, you know, if you accept a k plus one node clique missing a single edge that has a k clique inside of it, um, deciding whether to use k or n, or the size of s versus the size of the vertices doesn't matter. Um, yeah, I mean, does that help? And really, if you're not sure what delta should be precisely, oh yeah, no, I if you're not sure what delta should be exactly, um, but your intuition is that it should be close to one. Check that out and take your best swing at it, but give your intuition as well. Um, it's not something I would memorize. It's more it. How do you remember? It's not. Write it down on your cheat sheet. Yeah, I like that. Um, yeah, I wouldn't worry too much about getting delta exactly right. I mean, also give your logic behind it. Um, oh, I see. Um, yeah, I mean, if I would write down that pairs of points is v choose two. Um, anyway, once you figured out what delta should be, then your reduction, just passes through gk and the delta that you've computed. Um, and then again, you have the same steps. You have to show that your reduction is correct, and you show that it takes polynomial time in terms of gk. So in terms of the input to clique, which is also the input to your reduction. In this case, we're just adding a floating point number to it, so it's not a they're essentially the same size, but I just in general your input and output of the reduction could be significantly different sizes, um, and you need the reduction to be polynomial in terms of the input. And as long as your reduction is polynomial in terms of the input, then your output, yes, calculating the delta is included in the reduction time. All of the transformations you have to do is included in the reduction time. Like if we go back to reducing independent set to matching with forbidden edges, building the kind of exploded graph that took end of the fourth time to construct, that is included in the reduction time. But yeah, and even outputting GK delta is included. So because outputting out the output is included in the reduction time, your output will always have a polynomial relation to the size of your input. But if your reduction did not run in polynomial time, your output exponentially larger than your input. And then if you analyzed in terms of the size of the output, your reduction might be polynomial in terms of that, but that would not be valid. All right. Well, I'll leave it running for a minute or two to see if there's any more questions come in. But that's all that I'm running about 75 minutes now, and I covered everything that I'd written out ahead of time. So I think we'll stop here. All right. Okay, problem. Yeah, I can. Well, we need to prove reductions in both directions. You mean, yes, you need to prove, yeah, so I'll throw out, this is page 2 of what I did on the exam last time, once this catches up. So yeah, here I prove that if X is in clique, then the reduction belongs to the subgraph isomorphism, and I prove that if X is not in clique, then the reduction is not in subgraph isomorphism. So you prove both ways. Um, problem 9, thing at the end. Let's see. Yeah, so for like questions 5, 9, 10A, I haven't looked at those in as much detail because I was feeling like this would probably already take up the full amount of time, and it has. So I'm not going to try to cover that stream, but I will come back through and try to address your questions on Piazza. If there's questions, I can. If you have questions that are more detailed than you put in the Piazza thread, please just mark it. Reply with a follow up in Piazza with that elaboration, and I will try to catch up in that thread. But for now, I'm going to end this stream. Thank you all for tuning in, and seems like it was helpful for a lot of you, so I'm glad. And yeah, feel free to ask me any questions in Piazza, or on Slack. I don't mind if it's a question that other people can benefit from. Piazza is better because then it's visible to everyone and not just the people on Slack. Yeah, have a good night.